Hello and good afternoon. Thank you for watching. Today I'd like to discuss the block diagram of the PIC16F684 microcontroller. The block diagram provides a visual representation of the chip's internal architecture and functional units. Here's a brief overview of the key components and their functions. First, let's talk about the flash memory. Flash memory in the PIC16F684 microcontroller serves as a non-volatile storage for the program code and firmware. Here are the key points about the flash memory in the PIC16F684. Capacity. The PIC16F684 typically has 2 KB of flash memory. Non-volatile storage. Flash memory retains its content even when the power is turned off, making it ideal for storing the program code. In-circuit serial programming, ICSP. The flash memory can be programmed while the microcontroller is installed in the circuit using ICSP, enabling easy updates and modification to the firmware. Program execution. The microcontroller fetches and executes instructions stored in the flash memory during operation. Write and erase cycles. Flash memory supports a limited number of write and erase cycles, typically around 1,000 cycles for each memory location, making it suitable for infrequent updates. Read only during operation. While the microcontroller is running, the flash memory is typically read-only, ensuring the stability and integrity of the program code. Self-programming capability. The PIC16F684 includes mechanisms for self-programming, allowing the microcontroller to write to its own flash memory under certain conditions, which is useful for applications requiring firmware updates without external programmers. In summary, the flash memory in the PIC16F684 is a critical component for storing the microcontroller's program code, offering non-volatile, reprogrammable storage with in-circuit programming capabilities. Next, I'd like to talk about the program counter in the PIC16F684. The program counter, PC, in the PIC16F684 microcontroller is a crucial component of the Central Processing Unit, CPU, that helps control the flow of the program execution. Here are the key points about the program counter in the PIC16F684. Function. The program counter holds the address of the next instruction to be fetched and executed from the program memory or flash memory. Size. The PC program counter in the PIC16F684 is typically 13 bits wide, allowing it to address up to 8K words of program memory. However, since the PIC16F684 has only 2K words of program memory, the higher bits of the program counter are not used in this specific model. Incrementing. After fetching an instruction, the program counter automatically increments to point to the next instruction in sequence. Branching and jumping. The program counter can be modified directly as a result of program control instructions such as go to, call, return, and various conditional branch instructions. This allows for branching and jumping to different parts of the program. Reset behavior. Upon a reset, example, power on reset, brown out reset, watchdog timer reset, the PIC is set to 0x0000, causing the microcontroller to start executing from the beginning of the program memory. Interrupts. When an interrupt occurs, the current value of the program counter is saved to the stack, and the program counter is loaded with the address of the interrupt service routine. After the interrupt is serviced, the program counter is restored from the stack to resume normal program execution. Stack interaction. The PIC16F684 has an 8-level hardware stack for storing return addresses when subroutines or interrupts are called. The program counter interacts with the stack during call and return instructions. In summary, the program counter in the PIC16F684 is a fundamental part of the CPU that manages the sequence of instruction execution by holding and updating the address of the next instruction. It supports program flow control through automatic incrementing, branching, jumping, and interaction with the stack for subroutine and interrupt handling. Next, I'd like to discuss the 8-level stack in the PIC16F684. The 8-level stack in the PIC16F684 microcontroller is an essential feature that facilitates the execution of subroutines and interrupt handling. Here is a summary of its key aspects. Purpose. The stack is used to store return addresses when the program execution is interrupted by subroutine calls, call, or interrupt service routines, ISRs. Structure. The stack in the PIC16F684 is an 8-level deep hardware stack. This means it can hold up to 8 return addresses. Operation. Call instruction. When a subroutine is called using the call instruction, the program counter, PC, value, which is the address of the next instruction, is pushed onto the stack. The program counter is then loaded with the address of the subroutine. Return retfee instructions. When a subroutine finishes executing, the return instruction pops the top address from the stack back into the program counter, resuming execution at the point where the subroutine was called. retfee, return from interrupt, does the same but also re-enables the global interrupt. Interrupt handling. When an interrupt occurs, the current program counter value is pushed onto the stack before jumping to the interrupt service routine, ISR. After the ISR completes, the retfee instruction is used to pop the address from the stack, returning execution to the point where the interrupt occurred. Limitations. The stack depth is limited to 8 levels. This means that if more than 8 nested subroutine calls or interrupts occur, the stack will overflow, potentially leading to incorrect program execution. Automatic operation. The stack operates automatically and is not directly accessible by the user program. All push and pop operations are handled by the call, return, and interrupt processing mechanisms. No direct manipulation. Unlike software stacks in some other architectures, the stack in the PIC16F684 cannot be directly manipulated by the programmer. This helps in preventing inadvertent corruption of the stack contents. In summary, the 8-level stack in the PIC16F684 is a specialized hardware feature designed to manage return addresses for subroutine calls and interrupts, ensuring that the program can return to the correct location after these events. It operates automatically, providing a seamless mechanism for handling program flow control during nested calls and interrupt service routines. Next, I would like to discuss the RAM in the PIC16F684. The random access memory, RAM, in the PIC16F684 microcontroller is a vital component used for temporary data storage during program execution. Here's a summary of its key aspects. Capacity. The PIC16F684 typically has 128 bytes of RAM. Function. RAM is used for storing variables, temporary data, the contents of registers, and the stack during program execution. Data memory. The RAM in the PIC16F684 is part of the data memory space, which includes special function registers, SFRs, and general purpose registers, GPRs. Memory organization. The RAM is divided into multiple banks. Each bank contains both SFRs and GPRs. The PIC16F684 typically has 4 banks, but not all banks are fully populated. Bank 0 is the primary bank with the most commonly used SFRs and GPRs, accessing RAM. Although I thought there was only 2 banks. Getting my facts mixed up. Well, there's something to check on if you're listening. Anyway, accessing RAM. Access to different banks is managed through the Bank Select Register, BSR, or by using direct addressing. Instructions that access RAM include move WF, move data to a register, move F, move data from a register, and clear F, clear a register, and others. Special Function Registers, SFRs. SFRs are specific locations in RAM used to control the operation of the microcontroller, including configuration settings, I/O port controls, and status flags. General Purpose Registers, GPRs. GPRs are used for general data storage by the user program. These registers can store variables and intermediate calculation results. Indirect addressing. The PIC16F684 supports indirect addressing using the File Select Register, FSR, and the INDF register, allowing more flexible access to the RAM. Temporary data storage. During program execution, RAM is used to store temporary data, such as loop counters, function parameters, and intermediate results of computations. Volatility. RAM is volatile memory, meaning it loses its contents when power is turned off. Therefore, it is used for temporary data storage that does not need to be retained between power cycles. In summary, the RAM in the PIC16F684 is a crucial part of the microcontroller's data memory, providing temporary storage for variables, registers, and control data necessary for program execution. It includes both special function registers for control and configuration and general purpose registers for user-defined data storage. Next, I would like to discuss port A and port C in the PIC16F684. Port A and port C in the PIC16F684 microcontroller are general purpose input-output GPIO ports used for interfacing with external devices. Here's a summary of their key aspects. Port A. Pins. Port A typically consists of 6 pins labeled RA0 to RA5. Functionality. Each pin can be configured individually as either an input or an output. These pins are multiplexed with other peripheral functions, such as analog inputs for the ADC, analog to digital converter, and comparator inputs. Digital I/O. Configured as digital I/O pins, they can be used to read or write binary values, 0 or 1, analog functions. Certain pins, RA0 to RA4, can be configured as analog inputs for the ADC module. RA2 can serve as a voltage reference input for the comparator. Control registers. Trice A register configures each pin as an input 1 or output 0. Port A register reads the current state of the pins if configured as input, or sets the state of the pins if configured as output. ANSEL, ANSEL register selects whether a pin functions as a digital I/O or an analog input. Port C pins. Port C typically consists of 7 pins, labeled RC0 to RC6. Functionality. Similar to port A, each pin in port C can be configured as either an input or an output. These pins are also multiplexed with other peripheral functions, such as the serial communication interfaces and timers. Digital I/O. Configured as digital I/O pins, they can be used to read or write binary values, 0 or 1. Peripheral functions. Pins on port C can be used for various peripheral functions. RC0/RC1 can be used for timer inputs or outputs. T1OSO/T1OSI. RC4 can be used for serial peripheral interfaces, SPI. Data I/O, SDA/SDI. RC5 can be used for SPI data output, SDO. RC6 can be used for Universal Asynchronous Receiver Transmitter, USART transmission, TX. Control registers. Trice C register configures each pin as an input 1 or output 0. Port C register reads the current state of the pins. It configures as input or sets the state of the pins if configured as output. Common features: interrupt on change. Certain pins on port A and port C can generate an interrupt when their input state changes. This feature is useful for detecting events like button presses. Weak pull-up resistors. Both ports can have weak pull-up resistors enabled, which are useful for ensuring a defined logic level when inputs are left floating. Summary. And this is the summary of port A and port C. Port A and port C in the PIC16F684 are versatile GPIO ports used for interfacing with external components and peripherals. They can be configured for digital input or output and are multiplexed with several other functions such as analog inputs, timer inputs or outputs, and communication interfaces. Configuration is managed through trice, port, and ANSL registers, allowing flexible control over each pin's functionality. This video is getting rather lengthy. Stay tuned. Please subscribe as I continue to discuss the PIC16F684. Thanks for watching. Bye.
Block diagram, the flash memory functional unit microcontroller PIC16F684.